All right. Hello, everyone. Welcome. It is really great to see so many people here today. We are going to hop right in because we have a lot of exciting stuff to cover. First, some really quick introductions. I'm Allison. I'm a developer marketing manager here at Observable, and I am here with Observable founder and D3 creator Mike Bostock. We are really excited today to discuss and demo Observable's solution to the last mile problem in data. So as a quick preview of today's webinar, for the first 20 or 25 minutes, Mike will be teaching us about data's last mile problem and how we and you can overcome it by building data apps in Observable Framework. Then I'll spend about 10 minutes doing a quick live demo that shows how you can create, edit, and deploy a framework project to Observable. And that should leave us about 15 minutes for audience Q&A. So please feel free to share your questions in the chat during the webinar or once we get to that Q&A portion. So without further ado, I'm going to pass it off to Mike to teach us about solving data's last mile problem with Observable. Take it away, Mike.
Great. Thanks for the introduction, Allison. And thank you, everyone, for coming. Let me switch the layout here. So today we're going to talk about the last mile problem of data. And there are many variations of the last mile problem in different industries. But here we mean specifically the challenge of getting data from your data warehouse or your database or logs or wherever it lives to the screen so that you can look at it, explore it, answer questions, hopefully learn something. Because that's the point of data, right? To better understand what's happening and to make better decisions. The value we get from data is predicated on convenient performant access to it. If we can't get the data, or it's too slow to query, or lacks the detail we need, we won't get value out of it. So let's dive into this problem. Why is it hard to get data to the screen, and how can we make it easier? For this talk, first, I'd like to give a little more definition around this last mile concept. Then I'll talk about the practical impact of the last mile. Why does it matter if it's difficult to get data to the screen? And lastly, I want to share how we at Observable are addressing this problem with a new way of building data apps. So what do we mean by the last mile? Let's start with the original definition, as I understand it, of the last mile problem, which comes from the telecommunications industry. And I'm not a telco expert by any means, but this is my layperson's understanding. Telcos build networks. Like any business, they care about the cost of acquiring new customers. For example, how much does it cost to run fiber into a new subscriber's home? The last mile refers to connecting individual homes to the existing fringe of the network. In other words, connecting the leaf nodes as opposed to building the more central shared infrastructure. The last mile problem is the observation that the majority of cost of building a network comes from running this last mile. And this is really just a mathematical property of networks, because in a tree-like structure, the majority of nodes are leaf nodes. It's not a perfect analogy in data, but for us working with data, the last mile is getting data to the screen where it can be seen by human eyes. Typically, this means the browser issuing a query that runs on your data warehouse. So what makes the last mile difficult or expensive for data? Well, first, you may not have a data warehouse. Your data could be in a transactional database that isn't designed for fast analytical queries. Or maybe the specific data you need isn't in your data warehouse yet. Maybe it's in another database, maybe it's in logs, maybe it's in a third-party service API. Maybe it is in your data warehouse, but you don't have the right materialized views to query the data efficiently, so it's just slow. Whatever the case may be, it's often hard to get the data you need for visualization and analysis, especially if you want rich detail, and you also want your queries to be instant so that your viewers don't have to wait. Practical data engineering considerations can diminish the value you're able to get from data. So why is a difficult last mile a problem for data? I've already said it diminishes the value we get from data, our ability to derive insights. But to go a little deeper, I want to show two simple examples and demonstrate how access to data affects what we can visualize. Data in practice is complicated and varied. It's not just a neat array of numbers waiting to be fed into a line chart. It's a wild variety of tables and columns and formats and foreign keys. So data has to be refined into a suitable representation before we can visualize it. So as much as we may enjoy making pretty pictures, the bulk of the work of visualization is writing queries. It's deriving the data that goes into the chart. And furthermore, each chart is different. It requires different data and different data in different forms. So this is a time series line chart. It's probably the most common chart type you will see in a dashboard. This particular one shows the page views per day we get to the observable plot documentation. Plot is our open source visualization library that builds on D3. To collect this data, we have first-party analytics. We record a page view event in our analytics database whenever someone visits a page. The query for this chart groups those page view events by day and then counts the number of events per day. And then in the client, to draw these blue and white lines that you see overlaid, we use Plot's window transform to derive a 7 and 28-day moving average just to smooth out the weekly variation. This chart tells us a lot about the adoption of Observable Plot, the size of its community, and whether our docs are useful. You can see when we launched our new documentation, that was around May 2023, and we've seen about 4x growth in views since, so we're pretty happy about that. But daily page views is an example of a metric. It's a quantitative value that changes over time. And here that metric is derived by counting events in our analytics database. And for other metrics, we might use a different aggregate, right? We might use count of distinct users, latency quantile. There are lots of different metrics that can be visualized this way. But not all time series charts are simply a metric, a value that changes over time. At first glance, this might look similar to the previous chart, but the data is actually quite different. This is an issue burn down chart. It shows the open issues, and these are feature requests, bug reports to GitHub, again, for Observable Plot over time. But it doesn't just show the total number of open issues. It shows the age distribution of open issues on any given day. I didn't include a color legend on this chart. That was a mistake. But the older issues are purple on the bottom and the newer issues are red on the top. So you can see we still have a handful of very old issues, multiple years open at this point, as well as newer issues accumulating in red up there on the top right. The drop that you see there in February of 2023 was a pull request adding axis and grid marks to Plot. And this single PR closed more than a dozen feature requests because people love to have custom axes and grids to do their charts. I think that's actually a personal best for me in terms of number of issues closed in a single PR. And some of these were long-standing requests, right? The blue and dark purple ended up being closed with that PR. On the other hand, you can see, in the last few months, people are continuing to file new issues, but we haven't made as much progress in closing them. And that's because we've been focusing a lot on Observable Framework development. So this visualization requires different data than the previous chart. Rather than counting instantaneous events, such as page views, it counts overlapping intervals. An issue is created on a certain date and closed on a later date. For this visualization, most of the data transformation actually happens on the client. We render a tiny layer for each open issue that's colored by the date the issue was created and stack them on top of each other. If all we had was a count of open issues per day, like time series metric that you saw in the previous slide, we couldn't make this burn down chart. We'd lose visibility also into our productivity. We wouldn't be able to see which issues we're closing and what we're working on. So these examples specify how, or show how, specifying the data is really the core task of visualization. There's really just a table in the cloud that we can download to the client and visualize as is. Instead, there's complex filtering and aggregation and transformation to produce the needed data. And that means queries can be slow. And that's a problem because data apps typically run queries on load and users don't want to wait. And it takes work to optimize the data warehouse to make queries fast. In other words, data engineering imposes practical limitations on what we can visualize. So why not just make your data warehouse, instantly fast, make all your queries fast? As I said, it takes work. But there's another factor here, a more subjective, squishy, emotional one, which is that you're not going to do the work unless you know you need to, right? We're all efficient, rational actors. We want to spend our time on work that creates value. And the problem is we don't know what we're missing. If we don't visualize something because it's hard to get the data, we can't appreciate its value through the visualization. We can't assess whether it's worth the effort to get the data. So making data easier to access can profoundly change what we look at. It creates more opportunities to look at data. There's another challenge unique to data apps, which is that the language changes at the last mile. There are programming languages that are very popular for data analysis, Python, R, SQL, but JavaScript is the one true language of the web. So if you want to leverage the full graphics capabilities of modern browsers, you need JavaScript as well. Most frameworks target a specific language, but in data apps, we often want to use multiple languages together. Okay, so how do we make it easier to get the data we need for visualization? We need a new place to do compute. We can't do all the work in the client. That pushes too much data to the browser, and we'd have to write everything in JavaScript. And we can't do all the work in the data warehouse. Then we'd have to write everything in SQL, and it's a lot of work to optimize queries. Furthermore, we'd like our solution to live inside the data app, not our data warehouse, so that we can more quickly iterate and experiment. Our solution, which we encourage you to check out, is Observable Framework, a static site generator for data apps. And Framework's key architectural innovation is data loaders. Data loaders are programs. They can be written in any language, and they take snapshots of data at build time. This means that even if your data loaders are slow, it doesn't impact the user experience. When a user goes to view your dashboard, they'll load the already computed static data snapshot, which will be instant. Data loaders are tightly coupled with your application. They live inside your data app. So it's easy to iterate and experiment and get new data. Each visualization can have its own or even multiple data loaders, and you can use continuous deployment to rebuild your data as often as you need. Now I want to show you one of the ways that we're using data loaders at Observable. Observable itself is a web service. We get a lot of web traffic. We want our service to be fast because this means a better user experience. Like most web servers, they generate logs. We record those logs. We use Datadog, and these logs include the request latency, the number of milliseconds it took for the server to respond to these requests. This is how we were looking at API performance before, and this is a very standard practice, looking at P95 latency. So P95, the 95th percentile, means 95% of requests in a given time period were faster than the amount that you see at this line. And our P95 latency is about 200 milliseconds, but you can see some of those spikes there. Now, these spikes often occur in the middle of the night when traffic is low. And that's because the denominator is small, and so the metric gets noisy. This is really a terrible way of looking at server performance. The most salient aspect of this chart is noise. The reason that P95 isn't helpful here is because API traffic is highly multimodal, which means different requests are doing different things. Percentiles are great if you have normally distributed data. If all of your requests are computationally similar, the latency follows a smooth bell curve. But if some of your requests are cheap, they're doing different things, or they're cached, other requests are expensive, then a percentile tells you almost nothing about performance or about user experience. This is what we're doing now, thanks to Observable Framework and data loaders. Instead of just a summary metric, a number over time, we plot every single request to our API servers as a scatter plot. Technically, this is a heat map because the number of points is on the same order of magnitude as the number of pixels, but you can think of them as being equivalent. So on the x-axis, as before, it's time. This is a week's worth of data. On the y-axis is latency on a log scale. And we use a log scale because there's such a wide variation in how long requests take. You can have requests that take 1 to 3 milliseconds. You can have requests that take 3 to 10 seconds in the worst case. This is about 8 million requests. It's orders of magnitude more information being shown than the previous chart that you saw. And in fact, if you want to go look at this in your browser, you can go to observablehq.com right now, and you can just click on the Analyzing Weblogs example to follow along. Now, I love the detail in this chart. You can see how traffic volume varies throughout the day, throughout the week, and you can see these bands, right? These are different API endpoints that have different performance characteristics. And again, latency is not a smooth bell curve in most web services. There's a lot that's going on here. So let's add another layer to this graph to kind of give more detail. So now what I've done is colored the request by endpoint. So the before was just kind of a heat map. Now we can start to see different things are happening depending on what we're asking the server to do. Our API server has lots of different endpoints for doing different things. And because they're doing different things, they take different amounts of time. So kind of starting at the top, pink, this little pink band is listing notebooks, which at the time we collected this data, this is back in January, was relatively slow, around 1 second to list notebooks in a given workspace. Teal, which are like these streaky vertical lines here. I don't know, you can see my mouse here. Yeah, these like streaky vertical lines. Those are avatars. So those are like profile images for individual users or for workspaces. Those can also be quite slow. We'll get into that in a second, but you also notice that they're very streaky, right? You see these vertical striations that are happening. That means a lot of requests are happening at the same time for those avatars. Blue down here in the middle, this is compiled notebooks for imports. So you can import one notebook into another notebook. These are relatively fast. We use a lot of caching, and it's important for notebooks to be fast. Green down here, this is notebook contents, another way of loading notebooks. And then when you get down here, these are things like user authentication checks, which is essentially just validating a cookie or the lack of a cookie, and it's almost instantaneous, so less than 3 milliseconds. So we can filter this graph to look at a specific endpoint and understand that in more detail. So here we're going to look at the avatar endpoint, which I mentioned was very streaky. Loading avatars or profile images are especially slow because it can take several seconds to fetch a large image from S3 and resize it on demand to the requested size. Avatars are also spiky because a single page can load hundreds of avatars. In fact, some of these requests, some of these streaks are triggered by our own internal dashboards, where we're looking at, for example, new user signups or active users. So overall, avatars were the most expensive endpoint on our API server. And seeing this motivated us to make a number of optimizations. For example, we noticed that if you didn't specify the size that you wanted when loading an avatar, the API server would default to the largest possible size, which was the worst case scenario. It made it slower than it needed to be. And ultimately, we decided, we didn't even need our API server to be doing this work at all. We could move it to another service with better caching to improve performance and eliminate this work entirely. So let's look at another pattern that kind of sticks out here. These like green blobs here. So you see these kind of like daily blobs that are happening. Okay, that's weird. It's not normal because normally you expect your traffic to ebb and flow, kind of gradually increasing and gradually decreasing. Something is different about this when you see these kind of very clear, distinct patterns that indicates that it's not organic or natural traffic. And this kind of points out one of the things that I really love about this chart is that it doesn't just tell us about kind of the performance characteristics of our API server. It also shows us user behavior. Right, we're able to see patterns of external traffic coming in and weird things like this, which is a bot, as we'll find out, they stick out like a sore thumb. So I'm going to filter this now so you can see this is just focusing on 2 endpoints. So this lower one here, this is loading a document or a notebook at a specific version. And this upper one here is loading public documents so that we have like a recently published notebook feed. And so we did a little investigation into this. We think this is a research project at Northern Illinois University, according to the IP addresses, and they're doing public content analysis on notebooks. Generally, we don't like bots causing undue load on our servers, but we do also like to support visualization research. And the other thing, like this pattern here, so there's a daily pattern, there's also a monthly pattern where they do a deeper scrape of content. The other thing that I love about this is you can actually see as they are following these public feeds, the latency improves, so it gets faster. So the initial requests are slower, and then as they kind of get through and the servers have cached up the responses, they get a little bit faster. All right, so another example here. So what about this pink band that you see at the top of the chart? This is notebook listings, so listing the notebooks in a particular workspace, which at the time was a little bit slow. It was around 1 second. But there's something else kind of going on in this chart, which I think is interesting. So it's not sort of continuously at the same level of latency. There's this weird, again, daily pattern that seems to be happening where for like 2 or 3 hours every day, in the wee hours, it's slightly slower than it needs to be, or maybe even significantly slower, because this is a log scale, like twice as slow. Now, this one is weird because that increase in latency isn't really correlated with other traffic that's coming into the site. So it's not like there's a bot that's coming in and it's causing some interaction that causes these requests to be slower. And so the fact that that kind of slower latency isn't correlated with other traffic that we're seeing suggests there's probably some internal process which is causing extra load on our database. For example, we can have batch processes that do some sort of reconciliation or some sort of analysis, and that's probably causing overall load on the database, which then causes this to be slower. But we didn't really investigate this pattern too thoroughly because we just made the entire endpoint, I think, like 10 times or 50 times faster by fixing the indexing. It was slow because of some complicated permissions checks. But those things, like, really, they stick out like a sore thumb in this chart and help us prioritize what we work on. So one more example, this is an earlier snapshot of data. This is back in December, but it was an interesting pattern that we saw. So I don't know, you can see this like striation here. I think this is the content analysis scraper again. But the thing I wanted to point out was these kind of vertical yellow lines here. Okay, so if we just focus on that, that is an endpoint that was the stats endpoint, which got the number of views for a notebook. So we had a customer that was very interested in how much traffic their notebooks were getting, and they set up a bot to poll this endpoint for all of their hundreds of notebooks every 10 minutes. The thing was, like, we only update those stats once every 24 hours. So it was a little bit optimistic to get them every 10 minutes, but it was end up calling, tens of thousands of requests every day in order to get these stats out of our internal API, because this customer really wanted to know what sort of views that they were getting. So it's really useful to see these patterns in behavior, because it tells us so much, not just about the implementation of our API server, but how the world, how our users are interacting with that API server. Lastly, so I've been showing you, latency over time, but you can take any quantitative metric and look at that over time as well. So in this version of the chart, we're looking at the response size, so the number of bytes in the response rather than the number of milliseconds that the server took to respond. This one is interesting too, because these horizontal streaks represent specific popular resources. So this purple line at the top here, this is the D3 Gallery notebook, which is all of the D3 examples. That's one of our most popular notebooks. This green line down here, this is Jeremy's Inputs, which is a set of importable, reusable components that's very popular. So they're two different endpoints. Like, this is viewing a notebook and this is importing a notebook, but they're both popular, and you can see those striations. Now, you can't see it in this chart, but in an earlier version of this data, we noticed a bug. When you were signed out and you would visit a notebook, we feature some community notebooks in a footer below the notebook. And we normally show like 6 or 8 notebooks from the community. But we were mistakenly fetching 215 notebooks from a collection in order to load this little footer. And that made it a very large request. It was something like 50 kilobytes or something up here. And so those type of anomalous, like, performance problems, again, they stick out like a sore thumb in these charts. So, like, these charts have been super helpful for us. The irony is, the more we've been looking at the charts, the more boring they have become, because as we see something interesting, we fix the performance problem, we add caching, we block traffic that shouldn't be going to our API servers, that types of thing. So I think of these as spectrograms. You can have time along the x-axis and any quantitative variable you want over the y-axis. And then you see all of these really, like, surprising patterns. And we're only able to do this type of analysis because we can access the raw, unaggregated data in the client and not just summary statistics. Okay, so to wrap up, data loaders have been a huge breakthrough for us, and we think they can be for you also. Prior to data loaders, we had data in Datadog. It simply wasn't feasible to access the data in the client in this unaggregated way to make rich visualizations. We were limited to looking at simple summary statistics like percentile latency, and it would take 45 minutes to an hour to scan the logs to get a week's worth of data in order to produce these types of visualizations. So completely not feasible to do that on the fly when you went to visit a dashboard. Data loaders allowed us to take these complex queries and run them at build time and produce a rich dashboard that loads instantly. And this unlocked a deeper understanding of our API traffic, allowing us to make numerous performance optimizations. And to be clear, Observable isn't just a tool for analyzing web logs or even doing DevOps. This is just an example of how we use it for ourselves. You can use Observable, you can use these techniques and this architecture in any number of business applications and for any sort of data. So to summarize, data loaders help you overcome data engineering obstacles. It's okay to do dumb things and to use brute force. Data loaders let you quickly validate and share your ideas. It's not just a screenshot, it's a live dashboard that your team can look at. Data loaders mean performant data apps. It's instant because the data is a pre-computed static snapshot. And lastly, data loaders run the last mile. They make it easier to access data and power rich visualizations. All right, thank you everyone for listening. Please get in touch. You can reach out to me individually. That's my email there if you want to say hi. Please get in touch if we can help you build better data apps. And now I'm going to hand it back over to Allison for a hands-on demo of building with Framework. Over to you, Allison.
All right. Thanks, Mike. That was great. It was really fun to revisit some of those visuals because it was exciting even in our internal Slack as you were iterating. It seemed like almost daily there was a new insight from those visualizations about like, ooh, we could improve performance this way, or we shouldn't be accessing this many notebooks. So it was fun to see that really we were making changes truly almost daily based on that framework project and the iteration y'all were doing. All right, so I am really excited now that Mike has set us up with understanding the last mile problem and shown how we have benefited from using data loaders to get richer data displays and insights. I'm excited to do a quick live demo of creating an observable framework project, making some edits and seeing those changes in live preview, and then even deploying to observable. So I'm going to hop right in. All right, so I have open here the terminal, and the first thing that I'm going to do is create a new framework project. I'm going to use npm init at observable HQ. You could also use yarn commands throughout. I'm going to use npm commands in this demo. So once I run this command, then a really nice series of prompts come up to help me get started with creating my projects. I'm going to choose where I want this to live. So I'm going to give it a directory name. I will call this recent wind patterns. That'll become clear why I'm naming it that in just a minute. Then I'm asked what I want the title to be. I'll stick with this automatically derived title. You could always choose something different here. I am going to choose to include sample files. This is going to allow me to create a project right out of the box that I can see and tinker with. So I'll include the sample files. I will install dependencies here via npm. And then I'm asked if I want to initialize a Git repo. I'm going to choose no here, but remember that framework projects are just collections of files. So if at any point I did want to initialize a repo, I could just use git init using the same Git workflows and data workflows that I'm already used to. So now this is copying some files and installing dependencies. Well, it's working on that to create my project. Just a little preview of the data that I'm going to be accessing in a data loader in just a minute. I am going to be accessing recent wind data for the last day for a couple of different sites in the United States using NOAA's Tides and Currents Open API. So that's what we're going to be accessing in a data loader in just a minute. And it looks like now my project has been created. I can see that there's a nice message here. I want to switch over to the directory, and then I can open live preview. And I could do that here, but I'm actually going to do this in VS Code. This is my code editor of choice. You could edit and build framework projects in whatever editor you prefer. So I'm going to go ahead and open up this project, which I had put in development. I can see that recent wind patterns exists here. I'll open this and see that my project infrastructure has already been created for me. So there's some configuration files, a README that I can update. What we're going to focus on today is where most of your magic happens, which is where you're going to spend the most time building. And that is usually going to be in this docs directory within your project. First, I want to focus on these MD files. In a framework project, each page that appears when you build and deploy is created within an individual markdown file. So we have this index.md, that's going to be the project homepage. And also because we selected to create this with sample files, I have this example report and an example dashboard, each created in their own markdown file, which means they'll be their own individual pages. So I can see my files here, and I can, look at my markdown file to see what it contains. But I can't here see what this actually looks like. So when you're working in Framework, you can open your live preview server so that you can see exactly what your page is going to look like as you're making edits. So I'm going to use npm run dev, which is going to open my local preview server, and I can see that automatically my project is brought up on the screen, and I'll be able to see what each of my pages look like. So here's my home page. This is what's created in index.md. You can see there's a sidebar toggle automatically added. And I also have my example dashboard and my example report. So we can automatically, like out of the box with those sample files, see what this functional framework project looks like. Now, another thing that's really nice is that live preview will automatically update as you make changes in your project. So let's make a really obvious change. Back in this home page, I'm going to update this hero text, hello, Observable Framework, to instead say, hello, webinar friends. Now watch on the screen on the left where you see that hero text, because when I save in my markdown file in 3, 2, 1, then you will see that automatically that live preview is updated. So I always know exactly what my page is looking like as I'm iterating. So what we probably want to do, though, is we probably want to create our own new pages and access our own data so that we can make our own custom pages. So I'm going to go ahead and create first a data loader and access some of that WIN data, and then I'm going to create a page that accesses the data generated from that data loader. So I'll go ahead and in this data subfolder, I'm going to create a new data loader that I call wind.csv.r. Now, this double extension might look new. Data loaders have double extensions where the first extension, the CSV, indicates the output type that gets generated. The second extension indicates the loader type. So here what I'm creating is an R data loader that outputs a CSV called wind.csv, and that's what we're going to access in the page. So WinCSV, once I create that, I can go ahead and I can see my data loader created here. What I'm going to do is copy some existing R code. Keep in mind, I'm using R here. You can use whatever language you want. Python, SQL, JavaScript, Ruby, Rust, anything else. You can create a data loader in your language of choice. So I'm going to go ahead and copy my existing R code, and then I'll do a brief talk through of it. So in this R code, I see that I am just loading some R packages, reader and dplyr. I'm accessing some date times so that I can get the most recent WIN speeds and directions from that API, creating a URL. And notice here, because we'll come back to this later, notice that this station has a station number, and this we're going to start by getting the WIN speeds for a station near San Francisco. And then it does a little bit of wrangling before writing the output to standard output. That is the one thing that's true across data loaders, no matter what language you write them in. The output needs to be written to standard output to work with Framework's routing. So I am sending this data frame as a CSV to standard output, and then I can access wind.csv in my pages. Okay, so I've saved my data loader. Now I'm going to create a new page where I access the output, which is this wind.csv file that gets generated here. So back in my project, right in docs, I'm going to create a new markdown file. This will create a new page that I'm going to call windpatterns.md. Again, each page is in its own markdown file. So this is creating a new page in my project. Then I'm going to go ahead and in that file, I'm going to grab some existing code again. This code is going to access the output that's generated by that data loader. And then it's going to create a chart using our open source observable plot library for data visualization. So here you can see that I'm using file attachment pointing to this wind.csv file that's generated by the data loader using the same relative path that I would use to point from my Markdown file to the data loader itself. But notice that that .r isn't included. I'm just pointing to the generated output. I'll also add just maybe a little level 1 header up here that is called wind patterns. And now on save, now that that is accessing the output of that data loader, the data loader is executed, it finds wind.csv that's generated from it. And if I refresh in my live preview, I'll now see that I have this wind patterns page. And if I open that, then I will see a chart appear showing me the wind speeds and directions created in an observable plot for that station near San Francisco. Now, another nice thing is that we already saw that you can make changes in a page in a Markdown file, and that gets automatically reflected in live preview. But what's really cool is that you can also see changes that you make in data loaders reflected in live preview. So let's go ahead and say, actually, we didn't want to use a station in San Francisco. We instead want to use a site near Bar Harbor, Maine. So I'm going to go ahead and copy that station number for that Bar Harbor region across the country. Then I'm going to go back and update my data loader. So in my data loader, I'm going to go back to where the station number is specified. I'm going to paste in this Bar Harbor, Maine station ID. And now again, keep an eye on that screen on the left where you see this chart, because I'm going to save in 3, 2, 1, and we will see that the data loader is rebuilt. And we see that automatically now these wind speeds and direction for Bar Harbor are reflected on my page instead. So being able to update data loaders and pages and see the outputs change automatically in live preview gives you this really fluid and flexible way of developing apps, even like Mike was showing when you have really large data sets that you're working with. Okay, so to wrap up this demo, you might be wondering, well, where can I share this? And we recommend sharing on Observable. So you can really quickly deploy and host your projects on Observable. So I'm going to show you how you can do that, and then how you can take a look at what's created and what shows up in your account. So to do that, I'm going to run npm run deploy. Again, you could also use yarn commands here. When I run npm run deploy, then I can see that again, a nice set of prompts comes up helping me to deploy this project where and how I want to. So I'm going to deploy to the Observable demo team. I'm going to create a new project here. I'm going to use the slug recent wind patterns, which is derived from the project. I'm going to keep this a private project that only other workspace members can see. And I'm going to choose to build and then deploy. So build and then deploy. And then finally add a deploy message. So I'll say this is my initial deploy of this project. Now, after this is done generating the dist directory, the deploy is complete, then what we'll see show up right in my terminal here is a link to the live project. And that's a project that is hosted at observablehq.cloud. So you can see if I then open that, now, this looks exactly like what I was seeing in live preview, but this is no longer a live preview that I'm seeing. This is actually hosted from Observable, so I can see and share this project. And if I go to my account on Observable, then I'll see that this project now shows up there. I could see project analytics. I could keep track of the deploy history, and I can manage project access and settings. So it's a really nice way to deploy and share right through Observable. All right. So that was a little bit more of a jog than a walkthrough, but that gets you from creating a project through edits to deploy. If you want to do this on your own, we have a great getting started tutorial in our Observable Framework documentation, which we'll share in the chat. That lets you walk through step by step to create a new framework project, add a data loader, make edits, and then even goes through the process of deploy. All right. So that wraps up my live demo of creating, editing, and deploying a live framework project. And now we are going to hop into the last part of our webinar, which is audience Q&A. So it's been great to see some of these questions coming in already. So I'm going to hop back over. Me and Mike will be added. And we are excited to see your questions. Hi, Mike. All right. Okay, here's a great question that actually was bumped by a couple of other viewers. So I'll start with this one. So Elliot asks, is there a practical limit to the size of data that data loaders can handle? Or is it really just what the data loader build process can handle and what the client is willing to tolerate for loading?
Yeah, so I think for this question, it's important to distinguish between the data that is visible to the data loader, which is kind of the input to the data loader, and then the output to the data loader, which is what is actually loaded into the client. So for loading data into the client, for sure, there are some practical limitations to like how much data you want to ship to the client. We currently have a limit on 50 megabytes for deploying to Observable. If you self-host these projects, you can use larger limits, but generally speaking, you don't want to use, you don't want to ship hundreds of megabytes or gigabyte size files to the client. There are some exceptions to that. For example, if you're using Parquet as your output format. So Apache Parquet is a very efficient binary columnar representation. It supports range requests. So you can have a large file, but you don't actually load the entire file into the client. You just select a small slice of it. So there's a couple tools that can use that. For example, DuckDB WASM will take advantage of those range requests. If you're doing map tiles, there's a great binary format called PM tiles that's supported by Protomaps that would allow you to make range requests. On the server side or on the build time, like doing work in data loaders, there aren't really practical limits, I think, in terms of how much data you can work with. It's really more about how much data you want to set to the client. For example, if you're doing work inside of, or if you're using DuckDB's CLI inside of your data loader, it can very readily, load a multi-gigabyte CSV file and run a query against that in milliseconds. It's pretty astonishing how fast it is. But obviously, if you have like multiple data distributed across different machines, then it starts to get more complicated. And ultimately, that's work that you would probably be doing in a data warehouse. Like there's no practical limit on the size of your data warehouse. So I hope that gives a better sense. Like generally speaking, it of course is nicer if your data loaders are faster. That's more convenient for development. But the point is you don't really have to worry about it too much. If you can afford to have slower data loaders if you're just kind of getting things started and you're validating your approach, because you won't experience that slowness when you're actually looking at the dashboard or sharing the dashboard with your stakeholders.
Great. Thanks, Mike. And thanks for the question, Elliot. Okay, we have another one about data loader payloads from Sam. So I'll show this and then I'll hide this one after I read it so folks can see us again. So can you discuss strategies when you want to have more than one table available for your app that ultimately uses the same data source? If you want to make a query, for example, from your warehouse, but that original query, you want to produce two tables from that. I could create those two tables from the original table in JavaScript. Is there a way to have hierarchical data loaders, but still only make one call to your data warehouse?
Yeah, so there's a whole bunch of different ways that you can do this. I think the question kind of precluded one of the answers that I would give. So, one way is just to not worry about it and to have multiple data loaders that are running separate queries and they're producing separate tables. Like, as I mentioned, like you can load as many files into your page as you want to produce different visualizations, and they can all be based on querying the same data warehouse. But for other answers, so first is you can have what are called archive data loaders, and these archive data loaders produce either zip files or they produce tarballs like TGZ files or .tar files. And those are data loaders that can essentially produce multiple files. So it's a single program that does whatever it wants, can have a bunch of data in memory and produces multiple files as outputs. The cool thing is on the client, you don't actually consume those as a zip file or as a tarball unless you want to. You just reference files within those archives, and Framework will automatically pull the files out of the archive, and you can just think of them as individual files. So it's one program effectively producing multiple files. And this is really kind of a consequence of our design using standard out. So normally when you have a program that writes to standard out, we think of that as a single file, like you redirect it to a file or you pipe it to something. And in this case, we wanted to represent multiple files. And so we use these archive formats like zip archives or tarballs to represent multiple files. The last choice is, again, data loaders are arbitrary programs, so you can really kind of do whatever you want in them. So one of the techniques that we have done sometimes is to just essentially manage the caching ourselves. So I mentioned working with DuckDB. There's an example on the Framework website that visualizes data from the Department for Transport. It looks at reported collisions on roads in Great Britain. And the Department for Transport publishes a data set that has all of the collisions reported from 1979 through to 2022, I think currently. It's about 9 million reported road collisions. And it's a very large CSV file, as you can imagine. So we didn't want to load all of that data into the client. But also, as I was working on it, I obviously didn't want to keep downloading this like 1.2 gigabyte CSV file from the Department for Transport API. And so I wrote a data loader that essentially just cached that file locally. And so every time you ran it, if the file already existed on your file system, it wouldn't download it again. It would just use the existing file on disk. So you can do kind of whatever you want in order to optimize the performance. I do think we do have an outstanding feature request to support the concept of chained data loaders. So I think this will be something that we formalize and support in Framework in the future, because it is a fairly common use case to have these kind of intermediate data representations where you kind of first do one expensive query and then a bunch of other queries to kind of pull out the individual views that you want for different visualizations. So I think we'll add that. It doesn't exist currently. You can do it yourself though.
Great. Thanks, Mike. And thanks, Sam, for the question. Okay, next question is one that we've seen a lot. So let's look at this question from Jeremy, which is, once deployed on Observable, can you specify how frequently to run data loaders?
Yeah, great question. So we don't currently do managed builds on Observable, but we are looking at adding support for that. And it's definitely part of our roadmap because we want to offer this end-to-end solution. So currently the way that you would do this is you would set up your own continuous integration or continuous deployment, for example, using GitHub Actions, where you make a workflow file. There's a nice tutorial on our website. It's under deploying, and it talks about setting up continuous deployment using GitHub Actions. And you can, of course, schedule those to run as frequently as you want. So I think in common, I mean, it really depends, like how often do you want it to run? I think depends on your applications. So for example, for us, we do a lot of business intelligence stuff. We're interested in, how people are using the Observable product. A lot of those business intelligence decisions, like they take a while to execute. And so if you have a decision, like if you're making a product kind of strategy decision that could potentially take you several months to really affect, or to put into effect, you don't need to have a real-time dashboard. And you don't even really want a real-time dashboard in order to make those decisions. So most of our BI dashboards just run once a day using this continuous deployment strategy, but you can certainly run them, as frequently as you want. And we're even looking into kind of other ways to make this process faster. So having, effectively running data loaders continuously, or like if you want to run specific data loaders continuously in order to do incremental builds. And we have some thoughts around, so, you saw in live preview, you can edit a CSV data loader and it immediately pushes the changes to the browser. And so there could potentially be ways that we incorporate that into published sites as well. To do sort of more real-time data updates. So we're exploring those avenues. But yeah, right now it's mainly up to you, whatever continuous deployment schedule you want to run.
All right, great. Thanks, Jeremy, for the question. Okay, this one is from Paul, and this is returning to the API visualizations that you had created. So in those example charts you had showed earlier that they benefited from having access to the raw unaggregated data. Would this not be slow to load into the client when the raw data gets into the millions of points?
Well, I would encourage you to go visit the live examples because you will see like about a dozen charts, where it's loading, 8 million points into each of those charts and rendering them on the fly. So there's definitely, there are strategies that you can render millions of points without a problem in the client. One of the ways you should think about it is, drawing an image. Browsers don't really have problems drawing millions of pixels when they're rendering an image. So it's really just a question of how we render it in the client. As I mentioned, this is a heat map. So you can think of it as a scatter plot where it's drawing like 8 million points, but actually it's aggregating them into pixels and then, kind of doing some dynamic overlays with those pixels. That is a useful technique when you have, roughly the same number of points that you want to visualize as pixels you have on the screen. It just ends up being a more efficient strategy. So using these binary file formats like Parquet files or even Apache Arrow files. So Framework has a bunch of convenient built-ins to the file attachment API that make it more convenient to work with these file formats. You just say file attachment foo.parquet.parquet or foo.arrow.arrow, and it loads that into the browser so that you can work with it. So there are lots of different strategies for working with kind of larger data, and you have a lot of choices there. So I think for us, the practical limit wasn't really the rendering in the browser. It was like, how do we actually get the data? Because if it takes an hour to run the query over your logs, obviously that's not practical to work with.
All right, thanks. Okay, the next question is there a way to pass variables dynamically from the app back to a data loader?
Yeah, so the short answer is no by design, because data loaders run at build time and they produce static data snapshots. But there's a couple kind of variations to this idea. So the reason why it's kind of by design is that we really want to encourage apps to be fast. And that means that your data is already pre-computed. And so this idea that you would pass stuff dynamically means that you're running the queries dynamically on load, and it just tends to be a lot slower when you do it that way. So typically what we recommend is essentially you would compute the superset of data that you would want to send down to your app, and then you would query in the client. So for example, you can have a Parquet file that you generate with a data loader, and then you might use DuckDB to query and aggregate that Parquet file in the client to do sort of more dynamic exploration. So for example, we use this technique internally to do things like exploring our own database, looking at people that are using the Observable product, and we can essentially load summaries of all of the workspaces in Observable and then query them interactively in the client. And when you use these highly efficient compressed binary representations, you can get a lot of data into the client. So you don't really have to worry about kind of running each query individually, and you definitely don't want to run the query dynamically on load because it tends to be slower. That said, these are just web apps, so you don't have to use data loaders if you don't want to use data loaders. You can run dynamic queries against an API in order to fetch data dynamically as well. So it's really you have all of the things that you would normally have in a web application if you want to use those. I think it's more about us being opinionated and recommending that you favor doing static snapshots because it just ends up being a much better experience for your users.
Great, thanks, Mike. Okay, here's one from Angie. Maybe this will be a combo answer from us. What is the trick to make data loaders fast with large amounts of data? And how often do the wind patterns update from the NOAA server? Maybe I'll start with that wind pattern since I was working on that one. So when I created this app previously, I just automatically set up GitHub Actions so that it's scheduled to rebuild every 2 hours. But I could set it to whatever scheduling that I want to deploy elsewhere or on Observable. So then, Mike, I'll pass it to you for how we can make data loaders fast when we're working with large amounts of data.
So I think in some sense, the trick is that data loaders don't have to be fast because they run at build time. So if we're talking about the execution time of running your data loader, they can be slow. Like the example I gave, it took 45 minutes in the first version of our implementation of those API latency heat maps to run that data loader because it had to, page through many, many, many pages of this like Datadog logs API. So if we're really talking about client performance, how do we make it fast to load data into the browser? The answer is, it depends, but one answer is, sending less data to the client. So one of the advantages of data loaders is that they, as I mentioned, they're tightly coupled to the application, to the visualization that you're building, which means, you can do a bunch of processing, really make a table of data that's exactly what you need to make that visualization and nothing more than that. And so by reducing the size of the data, you kind of make that more performant. The other answer is, using these more modern binary representations like Arrow. The IPC file isn't really designed to send stuff over the web. That's what Parquet is for. But you can use either one. So Arrow files and Parquet files are both very, very efficient binary, or Parquet, I guess, is really the efficient binary representation. So that's how we're able to get, 8 million points into that scatter plot, is because we're representing it in this binary format that's both fast to load and fast to draw.
Awesome. Thanks, Mike. Okay, this gets us over our time. It's been really awesome to see your questions. If we didn't get to your question, please reach out to us. We are really grateful to have seen so many people join us in this webinar today. We want to say thanks to all of you for participating and for joining in the chat and all your comments and sharing your questions. So if you want to learn more or get in touch with us or request a demo and for links to our documentation and resources, you can find all of those through our homepage, which is shown here at observablehq.com, or reach out directly. We would love to hear from you about your questions, to show people how Observable can help them with their business insights and work and get more data, more value out of your data. So please reach out. We would be really happy to chat with you. So thank you again, everyone, so much for joining. Thanks, Mike, for teaching us more about the last mile problem and how Framework and data loaders help us to solve that. And we really will be excited to see you all again soon at our upcoming events. So thank you, everyone.
Thanks, everyone. Thanks, Allison.